Okay, good morning all of you. Yesterday I sent you one document by email, WhatsApp, as well as I posted the same thing on the Moodle, and it gives you some additional examples, okay, which are all self-explanatory. You can go through them, and based on that you can actually solve assignment problems. Here, this is one. This is the one which I sent you. You can see here an example is illustrated how to solve using variational method or Rayleigh-Ridge method. A boundary value problem is taken. One of the boundary condition is essential boundary condition. Other boundary condition is natural boundary conditions. How to get equivalent functional. You can go through all these steps. And at the same time, while going through the steps, you try to find if there are some mistakes, okay? And so you go through all these steps, and the first step, as we already discussed enough, a given differential equation, you multiply on either side with variation of the quantity that you are trying to approximate and integrate over the problem domain. And then second step is integration by parts. And then third step is use variational identities, and then see the term which can actually get eliminated or which vanishes based on the essential boundary condition that is given. Wherever essential boundary condition is specified at that particular point, variation of u is going to be 0. So applying all those concepts, that is what is explained in third step. Okay, and finally here even the fourth step continues the same thing. Finally, bring the given problem or the given boundary value problem into this form. Variation of something inside the bracket is equal to 0. Okay, and then whatever is inside the bracket, that is nothing but your equivalent functional for the problem. And then after getting this up to this, it's same as for classical methods and finite element method. And after this, it differs. Since the assignment problems are based on the classical methods, after this point, you need to decide what kind of trial solution you want to start with. Here it is illustrated with quadratic trial solution, quadratic polynomial trial solution. And so this is how quadratic polynomial trial solution looks like. You are already aware of it. And make it admissible by applying essential boundary condition. And once you get admissible trial solution, then you plug in that into this equivalent functional. And once you plug in into this equivalent functional is going to be, it's going to become function of unknown coefficients. So let's see, all that is illustrated here. All that is illustrated. Finally, equivalent functional is going to be, or it becomes function of unknown coefficients. Then apply stationarity conditions. And you are going to get so many equations as the number of unknowns that appear in the equivalent functional. To solve these equations, determine the unknown parameters, substitute that unknown parameter into the admissible trial solution, you are going to get approximate trial solution. And afterwards, after this, this is approximate solution starting with quadratic trial solution. If you want to see how it matches the exact, you need to plot it. You can plot the approximate solution as well as its derivative. That is what is actually illustrated here. This is how it matches. Same problem is also repeated using cubic polynomial trial solution. These are all self-explanatory. We just go through it's all mechanical in the sense no brainer is required. You just go through it, you will understand, and you please watch out for any mistakes if they are there in the whatever is presented here. Okay. So again, same thing is repeated with the cubic trial solution, cubic polynomial trial solution. That is a0 plus a1x plus a2x square plus a3x cube, and make it admissible by substituting the essential boundary condition. And then this is equivalent functional. For cubic trial solution in this particular problem, it turns out that this equivalent trial solution is going to be a function of three unknown coefficients. So to determine these three unknown coefficients, you apply stationarity condition, stationarity conditions, and you are going to get three equations, three unknowns. You solve for the three unknowns, determine the three unknowns, which are here a1, a2, and a3. A1, A2, and A3. Here there is a typing mistake. You can see such things. You please correct it. Okay. This is A1, A2, and A3. Once you get A1, A2, A3, you substitute into the admissible trial solution. You are going to get approximate trial, approximate solution, and you plot it. Okay. Another example is illustrated here. Another example is illustrated. You can go through that as well. And the notation is slightly different. Here it is written in a compact manner. Instead of writing d square u over dx square, it is written as u double prime. Compact notation is used here. You can go through all this. It's all straightforward, easy to understand. So you go through it and then check for any mistakes. On similar lines, you try to attempt assignment problems. Okay, so this is another example, and one more example is also illustrated here. One more example is also illustrated, which happens to be an eigenvalue problem, and I'm sharing with you this workout of this example because similar problems are there in assignment. So you can follow the similar procedure when you are solving assignment problems, and except this lambda is some it's like some constant. You can assume it to be like a constant. Except that the procedure is going to be similar to what you have seen. Okay, lambda is the eigenvalue that needs to be determined. So you when you are applying this variational whatever procedure that we followed in the previous example, when you are applying that, you just don't pay much attention to this lambda. You treat it like a constant. Automatically at the end, once you get the equations, it turns out it's an eigenvalue problem. Anyway, that is all illustrated in this example. This is the differential equation, domain over which differential equation needs to be solved. It is also given two boundary conditions. Both of them turns out to be essential boundary conditions. So you follow similar procedure. Take the given differential equation, multiply with variation of the quantity that you are trying to approximate, integrate over the problem domain, apply integration by parts, and then also apply the condition that variation of u is going to be equal to 0 wherever essential boundary conditions are specified, and based on that you simplify and you are going to get equivalent functional. Once you get equivalent functional, you assume some trial solution. Here again, the workout is given with quadratic trial solution as well as cubic trial solution. Here quadratic trial solution is taken, and then that trial solution you need to make it admissible by applying essential boundary conditions. And once you apply essential boundary conditions, you are going to get admissible solution. Take this admissible trial solution and substitute into this equivalent functional and apply a stationarity condition or stationarity conditions depending on the number of unknown coefficient that needs to be determined, and solve for here in this equation A2, you can see here, this is what eigenvalue problem looks like. A2 multiplied by this is equal to 0, okay? And you can see here for non-trivial solution. Non-trivial solution for this equation is possible only if lambda is equal to 10. What is meant by non-trivial solution? A2 multiplied by some quantity inside the bracket. A2 multiplied by some quantity inside the bracket is equal to 0. Okay, A2 multiplied by this quantity inside the bracket is equal to 0. Either the quantity inside the bracket should be 0 or A2 should be 0. Okay, either A2 should be 0 or this quantity inside the bracket should be 0. A2 is equal to 0, that is trivial solution. A2 is equal to 0 is trivial solution. So non-trivial solution is if this quantity inside the bracket is equal to 0. When that is going to be equal to 0? If lambda is equal to 10. Thus the approximation to the first eigenvalue of the problem is 10. And here please note that we started with quadratic trial solution, so we got only we can determine only one eigenvalue. Okay, and if you start with cubic trial solution, you can see the workout here and after applying this is the equivalent functional. After applying the stationarity conditions, you end up in getting these equations. These equations here, there are two equations. And if you want to solve it as an eigenvalue problem, better you put it in a matrix and a vector form. Okay, so this is how it looks like, and this kind of equation is familiar to you. Okay, it's of the form ax is equal to lambda times b, or ax minus lambda b is equal to 0, where a and b are matrices and x is a vector, lambda is some scalar quantity. Okay, so this is of that kind of form, and then you can solve this, and you can see here the trivial solution is A2 is equal to 0, A3 is equal to 0. I want non-trivial solution. If you want non-trivial solution, then you need to go back to your matrix analysis. Okay, and then you see if you have this kind of equation system, if you want a non-trivial solution, then whatever is there this in this brackets, okay, this matrices, this matrix minus lambda times this matrix, determinant of that should be equal to 0 if you want non-trivial solutions. So for based on that condition, you can determine you can solve lambda. And here the matrix, the system is 2 by 2 system. So when you apply this condition of determinant is equal to 0, you are going to get a quadratic equation in lambda. Like lambda is going to have 2 roots. You need to solve two values of lambda. Okay, those 2 values of lambda are going to give you the 2 eigenvalues. Lambda 1, lambda 2. Lambda 1, lambda 2 are the 2 eigenvalues. And if you want to determine corresponding to each of these lambdas, lambda 1, what is A1, A2? Sorry, A2, A3 here. If lambda is equal to lambda 1, what is A2, A3? You can determine. Okay, you can solve that. And you go back to your matrix analysis in your high school mathematics or +2 mathematics. Okay, this is all explained. And also maybe even some of these concepts you must have revised as a part of your first year engineering mathematics in your undergraduate courses. Okay, so once you get lambdas, your corresponding A1, A2, A3 you can easily determine. Here, that is what is mentioned. The corresponding eigenvectors are nothing but eigenvector is nothing but A2, A3. Corresponding eigenvectors can be computed by substituting the eigenvalues into the matrix system of equations. So this is how this eigenvalue problem can be solved. Okay, that is also illustrated by taking lambda is equal to lambda 1, by substituting lambda is equal to 10 here. How to solve for A2, A3, that is also illustrated here. So this is the first eigenvector and the second eigenvector. You go through it, and then if you have any questions, we'll discuss. You follow similar procedure for solving the assignment problems. Okay. And one more here, an example is also given here to illustrate the modified Galerkin method. Okay. And in modified in whatever I presented in the class in the lecture slides, I presented only up to this example is taken, and these are the boundary conditions for this. Up to this point only it is presented. And last class I also mentioned there is a typing mistake here. This should be x is equal to 1. This should be x is equal to 0. This is x is equal to 1. This is x is equal to 0. After this, how to proceed? After this, you need to decide on the trial solution. So here it is illustrated with a linear trial solution. This problem, this further simplification of this is illustrated here. Linear trial solution, that is the starting trial solution, and make it admissible by substituting essential boundary condition. U at x is equal to 0 is 0, and make it admissible. And once you get admissible solution, you plug in all the information here. Okay. Once you get admissible trial solution, what is in Galerkin method, how the weight function is defined? Weight function is trial solution, partial derivative of trial solution, or it should be admissible trial solution. Weight function is defined as partial derivative of admissible trial solution with respect to the unknown coefficient. That is how weight function is defined. So that is what is actually all the details are given here. You can go through it. Okay. W1 two weight function are here after substituting essential boundary condition, the admissible trial solution becomes U is equal to A1x, and weight function is going to be partial derivative of U with respect to A1. It's going to be x. And what is the weight function value at x is equal to 1 and x is equal to 0? That is all evaluated here, and you can go through it. Okay. So finally, this is what you are going to get: an equation and one unknown, one equation. You determine that unknown, substitute into the admissible solution. You are going to get trial solution or approximate solution. Okay. And once you get approximate solution, you can plot it and see how it matches with exact. So this we have not gone through the details in the last class when we were discussing about this modified Galerkin method, but here it is illustrated starting with a linear trial solution. Why linear trial solution is used here? Because we when we started out, or when we started discussing about this modified Galerkin method, we applied integration by parts, and the reason behind applying integration by parts is giving a justification that when we reduce the order of derivative appearing in the equation by one order, the demand on the starting trial solution gets reduced. So to illustrate that, earlier all examples are started out with quadratic trial solution, but here the highest derivative that is appearing is only first derivative. So even we can start solving this problem using, once we adopt modified Galerkin method, we can solve it using linear trial solution. That is the idea here. If the highest derivative that is present in this equation is second order derivative, then we cannot start with linear trial solution. Okay, that you have to keep in mind. And same problem is also solved using quadratic trial solution. Same problem is also solved using quadratic trial solution. And when you adopt this quadratic trial solution, accuracy may increase. Accuracy may increase. Okay. So here all that is illustrated. And same problem can also be solved using Rayleigh-Grigg method. You go through whatever is shared with you by email, WhatsApp, as well as whatever is posted on the Moodle. You please go through it. If you have any questions related to that, we can discuss. Okay. Any questions here? Any questions? Are you able to hear me?
Yes, sir.
Yes, sir.
But this one student is complaining no sound, something like that. So I did not see this comment. So from the beginning of the today's class, is there any sound problem?
No, sir.
No, sir.
No, sir. That the problem is from his end. Okay. Then this problem is from his end. I cannot help on that. Anyway, any questions? Any questions on the whatever I just explained to you? You just go through it and attempt the assignment problems. Okay. So if there are no questions, let me proceed further. So let me once again go through whatever we covered in last class. Okay. Even whatever I explained till now in today's class, that is all based on classical methods. And now we are switching over to finite element method. Please note that don't be of impression that the foundation that is laid by the classical methods, that is over which foundation this finite element method is built. It is based on the foundation that is laid by the classical methods. Okay. So given any boundary value problem with the domain specified, with the domain of the problem specified, and given boundary conditions, you need to follow the same procedure as you do for classical methods. Initial steps are going to be same. And for that you need to choose which approach you want to follow, whether you want to follow variational approach or Galerkin approach. And once you decide what kind of approach you want to follow, the initial steps you need to follow strictly whatever you learned as a part of classical methods. Even in classical methods, let me once again summarize what you have done. If it is Galerkin method, what you need to do is the given the given differential equation, you need to multiply with the weight function, integrate over the problem domain, and then if If it is modified Galerkin method, you need to apply integration by parts, simplify. All that is same. All that is same. Even for finite element method, all that is same. And one more thing, whenever we refer Galerkin method, hereafter, whenever we refer Galerkin method, that means we are referring to modified Galerkin method. Okay, but that is not applicable to assignment problems. In assignment problems, if it is mentioned solve by Galerkin basic formulation, you need to solve without integration by parts. And if it is mentioned modified Galerkin method, you need to solve it. But later in the sense, as we progress, whenever we refer Galerkin method, it means we are referring to modified Galerkin method, because we want to reduce the demand on the starting trial solution. Okay. Anyway, irrespective of whatever approach you choose, given the boundary value problem, the initial steps are going to be same. If it is variational method, the first step is, given differential equation, you multiply with variation of quantity that you are trying to approximate, which is u. Given differential equation, you multiply with variation of u on either side, integrate over the problem domain. First step. And second step is, try to see the highest derivative that is present. Highest derivative that is present, you try to reduce it as lower as possible. So next step is integration by parts. The third step is, wherever essential boundary conditions are specified, variation of u is equal to 0, apply that condition and bring the given problem into an equivalent functional, or express the given boundary problem as an equivalent functional. You try to find what is that functional, and if you do all that procedure for the problem that is given here, that functional is going to look like this. That functional is going to look like this. This is what I mentioned in yesterday's class as well. All those intermediate steps are not repeated here. So you need to verify. It is your responsibility to verify whether this is the equivalent functional for this problem or not. Okay? Whether this is the equivalent functional for this boundary value problem or not, it is your responsibility to verify. And also, there is an inverse procedure. Given the equivalent functional, suppose this equivalent functional is given to you. And what actually this equivalent functional, what kind of boundary value problem this equivalent functional is going to represent? That also you should be like, you think about it, because we don't have time to go through all that. Once you are familiar with all these steps here, how to get from the given boundary value problem to this point. If you want, suppose this functional is given to you, and you are blinded, and suddenly this equivalent functional is given to you, and you don't know where it is coming from, and you are asked to tell what exactly this equivalent functional is representing, what kind of boundary value problem this equivalent functional is representing. Then what is the procedure you need to follow? You need to follow the same procedure, except you need to take each time you need to take a step backward. Okay, let me show you that. Maybe for completeness, let me show you that. So now let's take an example here. So this is a boundary value problem, and these are the boundary conditions, and this is how we go. First step, second step, and also apply all the variational identities. Okay, and this apply using the boundary conditions, simplify the boundary terms, and finally you got this. Finally, you got this one. equivalent functional for this problem. So now what I'm saying is, suppose this equivalent functional is given to you. Can you tell, or can you tell that whatever that equivalent functional represent this boundary value problem? How to get back to this? How to go in the backward direction? If you are familiar, or if you are comfortable in going in the forward direction, you can easily go in the backward direction. But it takes time, okay? But that kind of knowledge is very much essential. Just I want to emphasize on that. It's not that you need to do it, but later when you are trying to understand this finite element method or any of the numerical methods, that kind of exercise is very, very important. So now let's say, if this equivalent functional is given to you, what is the first step? The first step is apply variation operator on this functional. Apply variation operator on this functional. That is how this step is applied. That is how this step is applied. I'm going in the backward direction. Once I get this one, you expand it. You open the bracket and then apply the variation operator in each of the terms. On each of these terms. Okay? And then apply the variational identities. Apply the variational identities. And then bring it into this form. Okay? When you bring it into this form, because you are coming in the backward direction, when you come to this point, one of the boundary condition is going to be, one of the boundary term is not going to be there when you are coming in the backward direction. At that time, you can guess why it is not there, why it is missing there. Then that gives you an idea about what is the essential boundary condition. What is the essential boundary condition? And then other term is going to give you an idea about the natural boundary condition. And finally, once you come to this point, you can go back, you can apply integration by parts in the reverse direction, and then get to the first step, and then you can easily identify what is the differential equation it represents. So that's why I'm saying you should be very comfortable in applying these variational identities, integration by parts, all these concepts, both in the forward direction as well as in the backward direction. Both in the forward direction as well as in the backward direction. Okay. So why, for completeness, I explained to you all this, because in some textbooks they give some kind of explanation for this as well. If this functional is given, equivalent functional, you should be able to guess what boundary value problem it actually represents. So in summary, this equivalent functional is going to be unique for each of the boundary value problem. It's not going to be same. Okay. Anyway, that is story about this equivalent functional, how to go back and forth on this. Okay. So now let's come back to whatever we discussed in yesterday's class. So this is this equivalent functional. Once you get it, and now that is where the deviation is going to come. In classical methods, what you are doing is you start with a quadratic trial solution or a cubic trial solution or a linear trial solution, make it admissible, all that. But in finite element method, what we are going to do is this domain 0 to 1, I'm going to discretize it. I'm going to divide it using m number of elements and n number of nodes. And that is what is actually depicted here. That is what is here shown. And a typical two-node element looks like this. Typical two-node element looks like this. Let's say that element is ith element. Length of that typical ith element is Li. and the first node the coordinate is xi, and the second node coordinate is xi plus. This all we discussed in yesterday's class. I don't want to repeat too much on that. Okay. So if this is a typical two node element, and one of the difference between classical methods and finite element method is, in classical methods you have these unknown coefficients a0, a1, a2, something like that. They are all simply mathematical quantities. In finite element method, we want to bring some physical meaning to those quantities. So that is what is actually to address that. This is how it is actually done in finite element method. If you have 2 points in space, and the simplest way you can join these 2 points is by a straight line. Equation of a straight line can be represented as y is equal to mx plus c, or same thing is written here. And let the variable that varies over this line be u. So u is equal to a0 plus a1x. It's similar to y is equal to c plus mx. It is written in this manner. U is equal to a0 plus a1x, and x varies from xi to xi plus 1. If x is equal to xi, u is equal to ui. If x is equal to xi plus 1, u is equal to ui plus 1. So you get 2 equations. Express these unknown coefficients a0 and a1 in terms of the u value at ith node, u value at I plus 1th node, and the geometric coordinates. Okay, and if you do all that exercise, a1 turns out to be this, a0 turns out to be this, and substitute this a0 and a1, into the starting equation. Once you get a0 and a1, you substitute that information here and group the terms having ui separately and ui plus 1 separately. Group the terms having ui's coefficient separately and ui plus 1 as separate. And if you do that separation and write it, this is how it looks like. U as a function of x is equal to this. And you can see here, whatever u as a function of x, you can see it is still a linear in x. It's this quantity is linear in x, this quantity is linear in x, and this addition sign. So the total equation is linear. And we started with a linear equation. We re-expressed whatever check I told you. You just that kind of check helps you to see if you made any mistake. Okay, so this is also linear. So this term, whatever is there here, that is denoted with ni, and this second one is denoted with ni plus. So this equation can be compactly written as u as a function of x is equal to ni ui plus ni plus 1 ui plus 1. Okay, or it can also be written as here capital sigma symbol. You may be familiar with sigma, capital sigma, Greek letter. You can just simply say sigma ni ui. U is equal to sigma ni ui. When you write it in that manner, I loops over all the nodes over that element. I loops over all the whenever there is a repeated indices, and that is what is called Einsteinian notation. And if you take any course on continuum mechanics, you'll be using that kind of notation. Some textbooks simply write ni ui in the sense that actually ni ui plus ni plus 1 ui plus 1. Okay, so that is a compact notation that you keep in mind, because if you are referring different textbooks, they may be using different notation. Anyway, this equation can be compactly written like this. And now, also explained to you in the last class, in each of the element, u is varying linearly. This is ith element, this is I plus 1th element. This u value at ith node is ui, at I plus 1th node is ui plus 1, at I plus 2 node is ui plus 2. In between in this element I, it's going to have linear variation, and in this I plus 1th element also it's going to have linear variation. Only thing is slope of it may be different. So if u is like a displacement, u is going to be piecewise linear in the sense this is one piece and this is one piece. Piecewise continuous. It's called piecewise continuous. This is one piece and another piece at the common point. At the common point, displacement has to be same. If it is not same, if the displacement is not same, then there is going to be discontinuity. Imagine your train. In a train, it has several bogies. Each of the bogie is linked at some common at the point of wherever link is there. Each bogie, the displacement should be same. If the displacement is not same, then the train is not it got broken somewhere. So there is a failure of link between the bogies. So like that, the common point you are going to have same displacement between the elements, but the variation of displacement in each of the element is different, and each of the element will have different variation in the sense strain is going to be different in each of the element. When you take partial derivative of u with respect to x, if u represents displacement, partial derivative of u with respect to x represents strain. Strain is going to be discontinuous and strain is going to be constant. Strain is going to be constant in each of the element. For when strain is going to be constant? For a two-node element. For a two-node element, strain is going to be constant, and at the element boundaries, strain is going to be discontinuous. If strain is discontinuous, stress is also going to be discontinuous. Okay, so these points you need to keep in mind. Any questions here? Any questions? So now let's come back to, this is all what we covered in last class. This is all what we covered in the last class. And now we expressed, what we did is instead of writing u is equal to a naught plus a1x, we came up with a different kind of writing the same thing. U is equal to ni ui, ni plus 1 ui plus 1, where ni is the shape function or interpolating function corresponding to ith node. Ni plus 1 is shape function or interpolating function corresponding to I plus 1th node. And ui is the value of u at ith node. Ui plus 1 is the value of u at I plus 1th node. So instead of writing u is equal to a naught plus a1x, it is written like this. And once we have this, rest of the procedure is same. We need to go back to this one. We need to go back to this equation, and we need to plug in this one. Okay, and before we do that, please note that this is for ith element. First, we need to decide how many elements we want to use. So for that, we are going to write the previous equation in a slightly different manner. Instead of integrating from 0 to 1 at a single stretch, we are going to integrate from starting from some value, let's say 0, and going to some value. And instead of integrating from 0 to 1, we are going to integrate over several pieces. Okay, so this equivalent functional, we are going to slightly write in a different way. And before that, these two terms are associated with the boundaries. Boundary in the sense x is equal to 1 is boundary. So this is a boundary term. This term is associated with boundary. This term is associated with boundary. That you need to keep in mind. Okay. So now let's focus on this one. So instead of integrating from 0 to 1 in a single stretch, this one we are going to integrate from x1 to x2, x2 to x3, n minus 1 to xn like that. And whatever is there in the bracket that is defined as f, because I don't want to write this a big quantity every time. So that is the reason it is denoted as f, and then this equation can be written like this. So now once we write in this manner, so now we need to decide how many elements we want to use. So let's start with one element. So this entire 0 to 1, this entire 0 to 1 domain is discretized or divided with one element. Divided with one element. So the first node of that element is going to be at x is equal to 0 or x1. X1 is nothing but 1 is to denote this is first node. And the second node, there is only one element, one two-node element. Two-node element has two nodes. So this is the second node of the coordinate of second node of element, which is x is equal to 1. This is 0, this is 1. This entire domain is divided into one element. And u value here is u1, u value here is u2. You please take a note of it. And now write this trial solution. What is the trial solution now? It's going to be u as a function of x is n1 u1 plus n2 u2. How to get n1? How to get n2? You need to use the previous equations, ni plus 1. So based on that, n1, n2 are obtained. Once n1, n2 are obtained, you substitute that here. And also for this problem, essential boundary condition is given. U evaluated at x is equal to 0 is 0. U evaluated at x is equal to 0 is 1. U evaluated at x is equal to 0 is 1. So you see the problem here. U evaluated at x is equal to 0 is 1. That means u1 is equal to 1. You plug in that information. So then finally, once you do that, all that simplification, u approximate solution is going to be u is equal to 1 minus x in bracket plus x times u2. And you take derivative of it, because in the equivalent functional, u prime is there. You take derivative of it, you get that. So once you have all this, you plug in here. And also here, u evaluated at x is equal to 1. What is that means? This is nothing but, this term is nothing but u2. And this term is nothing but u2 square. Okay, you please take a note of this. Quickly take a note of it. I'm going very slow. Understand? This is all a repetition of last class. The idea is I want you to understand clearly. So you take a note of this one. So plug in all this information. Wherever u prime is there, you plug in this one. Wherever u is there, you plug in this quantity, this one. And this u evaluated at x is equal to 1 is nothing but u2. This is u2 square. Substitute all this information here and do the integration and try to find what is this equivalent functional. And if you do all that, equivalent functional looks like this. Apply stationarity condition. Partial derivative of u with respect to u2 is equal to 0. Determine u2. Substitute u2 into the approximate solution. Approximate solution is this one. Approximate solution is this. U1 is 1, already given essential boundary condition. Just now U2, you found it is 3 over 4. You substitute, this is the approximate solution. And this is the derivative of that. So this is this approximate solution we obtained using one element. This approximate solution we obtained using one element. I'm not, let's say you are not happy with this solution. This is a, please note that this is an approximate solution. There is going to be an error associated with it. And if you want to check whether this solution is correct or not, you take, instead of one element, you take two elements. So the same procedure, if you understood this one, if you understood this procedure for one element, you can extend it for two elements. Two elements in the sense, I'm going to take two elements. First element is going to be from 0 to some midpoint. You decide. Let's say midpoint between 0 and 1, which is 0.5. So first one element is going to be from 0 to half. Second element is going to be from half to 1. For each of the element, you need to write the trial solution. You need to determine what is N1, N2 for each of the elements, and you need to write all this for each of the element. And here, when you select two elements, you are going to have node 1 here, node 2 somewhere in between, node 3 is going to be this one. So this term, these boundary terms are going to get modified as U3. You evaluated at x is equal to 1. Now you are using 3 nodes, so x is equal to 1 corresponding to the third node, so this becomes U3. So all that, taking note of all that, if you this is how for one element solution, how the u value is looking like a derivative of u. And please note that first of all, why we are going to solve a problem. Why we are going to solve a problem? Real problems, when we are going to solve, when we don't know the solution. It's not that all the time we know the solution. We are checking how finite element is going to perform. It's not like that. For unknown problems, for the problems for which you don't know the solution, if you want to use finite element method, you need to do finite element analysis using refining the starting with less number of elements. You keep on increasing the number of elements. You see how the solution is converging. So finally, once the solution is converging, that convergent solution, you can take it as solution to the problem. That is how you are going to solve the real problems. Okay. So now, so we here for one element, whatever solution you got, the u value derivative of u is plotted, and this two element solution workout is shown here. Just I am going to stop in a minute. Okay. Two element solution. So two element means there are two elements. First element is going from 0 to half. Second element is going from half to 1. It's not necessary that both the elements should be of same length. You can have first element going from 0 to 0.25 and second element going from 0.25 to 1. Okay. So here it is selected both the elements having length is equal to half. And for each of the element, trial solution is written. You just go through it, and essential boundary condition is given. U evaluated at x is equal to 0 is 1. X is equal to 0 corresponds to node 1. So U1 is equal to 1. Okay. So all that information is substituted. This is trial solution for element 1. The u value derivative of u, trial solution for element 2, u value derivative of u. Using these trial solutions, you need to write equivalent functional instead of integrating from 0 to 1 in a single stretch. Now we are going to integrate over each of the elements, 0 to half, half to 1, and this is that integrand, whatever is there. Okay, and these are the boundary terms. So now x is equal to 1 corresponds to u3. X is equal to 1 corresponds to u3. So instead of u evaluating that x is equal to 1, u3 is substituted here, u3 square is substituted here. And you have u value and u prime value for element 1, u value and u prime value for element 2. You plug in that information here for first element, second element, simplify this integral, and u is going to, this equivalent functional is going to be a function of u2 and u3. Because u1 is already given. u1 is essential boundary condition. It is 1. Apply the stationarity conditions. Solve for u2, u3. Once you get u2, u3, you plug in into the approximate solution. Approximate solution. How do you get it? Approximate solution. You have the expressions for element 1 separately, element 2 separately. Once you get u2, u3, u1 is already known, u1 is equal to 1. You go to element 1, simplify, element 2, you simplify, plot it. You can see here, at the junction of the two elements, displacement is continuous, but it is having slope difference. In element 1, slope is different from element 2. And when you take the derivative, you can see here jump is there. Okay? So this is 2-element solution. And if you want, you can extend it 3-element solution. Okay, like that. So now you plot 1-element solution, 2-element solution, 3-element solution, how it is matching. You can see here almost 2-element, 3-element, they are going in a converging trend. Okay, if you go for 4-element solution, it's going to be much closer. So this is how convergence is happening for u. Whereas derivative of u, I told you one thing in the last classes. Taking differentiation. Differentiation is a rough process. When you try to differentiate a quantity, convergence is not going to be obtained as quickly as possible. So derivative of u, it takes some time to converge. Some time in the sense, more refinement is required to converge. Whereas here, u is almost converged from 2-element to 3-element. Okay, so think about it. We'll discuss further in next class. Okay, so I'm going to stop here. Please take assignment problems seriously, and let me stop sharing. And here, which method will give accurate solution? I don't know what do you mean by that. Let's discuss that in tomorrow's class. More number of elements with linear trial solution or less number of elements with quadratic cubic trial solution. That's what I'm saying. The idea is you better use lower order elements. Okay. And whether more number of, anyway, obviously when you use lower order elements, you require to use more number of elements. Okay, and we'll see this. Whatever question is posed here, you will get an answer to that in the subsequent classes. Okay, let me take attendance. Okay, thank you.
Thank you, sir.